Thank you very much indeed. It's always like a family reunion or something when I come back to Dublin. Have been here many, many times, and it is eons ago that I met people here that I now meet again. But I've actually also talked about histograms and about Prometheus before, and it's like some conference archaeology here because this is me here. In SREcon 2015. Europe, it wasn't called EMEA back then. I don't know what that was about, but this is a talk about Prometheus. And this was, this SREcon was the first SREcon in Europe, and it was the third SREcon ever, and it was the first conference ever that had a Prometheus talk. So this was essentially where Prometheus got presented to the world for the first time. And of course, Julius had to be there as well. He is actually one of the founders of Prometheus, which started in 2012, but in 2015, we dared to give a conference talk. And why am I telling you all of this? There was a Q&A, and you probably know this person. It's Brendan Burns, another founder of something, founder of Kubernetes. And he was very enthusiastic about Prometheus. And he asked, literally, do you guys support histograms? That was his first question in the Q&A. So it was a hot topic already back then. And my answer, a colleague of mine found that for me, my answer started with histograms, my favorite topic. So I have been very consistent about this. It's still true, it's still my favorite topic. So here are the building blocks of this talk. SRE, of course, SREcon. Prometheus, I guess most of you would agree, it's a toolbox. It's a tool in the toolbox of an SRE, and histograms are also a tool in the toolbox of SREs, and there's a special relationship between those two. In case you want to watch the historical talk, there's the link. You can download the PDF later from the conference website, and there are lots of links in this talk. It's kind of a viewing guide for other talks, 50% of it. And I also want to refer to a talk that we had yesterday, right? So there was the workshop, Statistics for Engineers by Heinrich, who is also here in the room. Maybe you have been there, and maybe, pretty sure histograms were a topic there as well, just proving that histograms are important for our profession. Also, this Statistics for Engineers workshop, this happened always, right? The 2015 SREcon also had Heinrich's workshop, Statistics for Engineers, if I'm, he nods, so it's correctly remembered. So we are all very consistent here. Okay, histograms. You can do loads of stuff that is important for SREs, and I just put random stuff on here. There are those questions I put there that are really very specific, but you can answer them if you have histograms somewhere collected in your metric system. You can draw beautiful heat maps, which tell you a lot of stories. Uptake score, I don't know if that's still a thing in these days, but maybe, I don't know. Usually you calculate an uptake score backed by histogram. SLO, definitely a hot thing now. And often SLOs are formulated as in, I want to serve 99% of requests correctly and within 500 milliseconds. And that is just perfectly tracked by a histogram. And I wrote correctly aggregated quantiles here because that's something that also people like Heinrich are preaching all the time, all the mathematicians. There is, I think we learned this lesson, but traditionally instances in a distributed system would just expose a pre-calculated quantile, like my 99th percentile latency is X, and then people collect this from all the instances and they just average them and are unaware that this is mathematically complete nonsense. And to do correctly aggregated quantiles, you need some kind of histogram or histogram digest that is actually mergeable, and then you can collect from all of this. And histograms are, again, a solution at least for this. Okay, so the histograms we had in Prometheus back then, they solved those questions. There are problems, but at least they gave you this mathematically correct approach, and it wasn't, I don't think there was anything like this in the open source world. This is how a histogram back then looked like. It's deliberately fine print, so you don't have to read it all, but there are like underscore bucket series. These are like the buckets of the histogram. Every bucket becomes its own series, and there's an underscore count to count observation, underscore sum to sum up observations. And the whole idea behind this is that the Prometheus data and execution model was just based on time series of floats. Timestamp floats, just put all in a line. And you had to break down this complex thing that is a histogram into this model, and you could just break it down by having every bucket into a series. And it was magical because we didn't really have to modify anything in Prometheus. We just needed to add a single new function to PromQL, which is called Histogram And with that, we could answer all those questions. I always thought this should be seen as like a proof of concept or a prototype or something. But it worked well enough somehow, so we kind of got stuck with it for many years. And of course, there were other things to work on that might have been more pressing. But here are the problems. So you need to define all those buckets in advance. And that's really annoying. If you've ever done this, you probably were annoyed by it. There's one of those Prometheus proverbs that I like, or maybe I coined it myself, I don't know. Instrument first, ask questions later. And here you actually have to already know what latency buckets you're interested in. And if you then realize I'm actually interested into a different latency bucket, you have to change the predefined buckets, which is really painful because you have to re-instrument, redeploy everything. And also it breaks aggregation. I mean, I just bragged about correct aggregation, but if your bucket layout changes, you could do it in a very specific, smart way, but most of the time it means your aggregation doesn't work any longer with the older histograms, which I call aggregation across time. But also you might have older versions of your binary running in production, and the canary is the new version. Then you can also not aggregate between those instances, which I call aggregation across space, right? Aggregation across time and space. It sounds like very sci-fi. So buckets are also expensive. I mean, Prometheus is very efficient, but it comes at the price that a series is kind of the heavyweight element in the database. Like adding more samples to a series is super cheap, but adding a new series is relatively expensive. And now every single bucket creates a new series. And because they are so expensive, you cannot have high resolution. And because they are so expensive, you also don't dare to partition your histogram by labels. I mean, label partitioning creates this cardinality explosion. We all know this. And now it's again multiplied by the number of buckets, which could be like 10 or 15 or something. It makes everything worse. Okay, so I knew we had to do something, but it took many years. Okay, sorry. Before I lament about this, let's check how it looks like. This is what you usually do as kind of a workaround. You instrument, it's Go code, you instrument a counter that is partitioned by the status code, or more like method or whatever you want. And that's a relatively cheap thing. It's just one series per whatever you have. And then you have a moderately expensive histogram here with 11 buckets. And you don't dare to partition that. It also gives you a hidden plus infinity bucket and the sum and the count. So it's 14 series per histogram, and if you partition this by whatever 20 status codes, it gets all very expensive and bad. Okay, so we had this. It was kind of getting us along the way, but I always wanted to do something about it. But for 5 years, there were always distractions and other stuff happening, and also whatever. Long story, it was the year 2019 or 2020 when I actually started to seriously do something about it. And of course, I gave talks about it because I like talks. And this is what I call the original trilogy. So you can, again, download the slides and watch them all. The viewing order is different from the order they appeared. So it's like prequels, whatever. But like it's the past, where do you come from? Then the PromCon2019 in Munich was, what is the plan to do now? And then finally, how does it even work? This was a KubeCon talk. No, why does it work? That was actually a lot of serious research why the approach actually works. And then we came up with something we now call native histograms. Had different names in between, was a bit confusing, but native histograms is the proper name, and it also stuck, I think. Okay, this talk is supposed to tell you hands-on how to work with native histograms, so I'm not going into the details too much. It's kind of headline style. What are the features? And the one important feature that also created this name is that we have a native, aka first-class treatment of histograms as samples. So one sample, traditionally, it's just a floating point value with a timestamp. And now it's a time-stamped histogram with all the buckets and the count and the sum in one sample as a structured thing. And that means now every histogram is just one series, finally, right? This allowed us many things, but the most important things are probably that now if a bucket is empty, we don't have a series that has just like, I mean, it doesn't even have zeros in the original approach because they are cumulative, but whatever. Like now we have empty buckets that have just no cost at all. They just disappear, right? Or an empty bucket, I mean, we essentially have buckets everywhere, but when they are empty, they are invisible. And in a longer line of argument, it arrives at the conclusion that this allows affordable partitioning by labels. I wanted to explain this in the talk, but took too long, so you can ask me later about partitioning by labels. Why does this zero cost empty bucket allow this? I mean, it makes it affordable, right? Okay. Also, we wanted never ever you want to configure buckets again, so minimal configuration. We have an exponential bucketing schema with dynamic resolution. That sounds really cool. So it covers the complete float 64 space. I mean, it's a lot of buckets, of course, but if they're empty, they don't exist. And when something pops up somewhere, we just create a bucket for it. And the resolution can go up and down by halving and doubling buckets. And this ingenious, I mean, it's actually pretty easy mathematically, but this ingenious bucketing schema allows us to always aggregate histogram across time and space, as I like to say. And high resolution is now affordable because everything is more efficient. And in a benchmark, I came to the catchy conclusion, you get 10x the resolution at half the price. That's more or less how the efficiency works out. And that maybe is the most important thing in the end. We just talked about it here before we started. It is compatible with the new histograms in OTel land. And we did a lot of behind-the-scenes communication to make sure that we don't accidentally create little knots there that are not compatible for some accidental reason. So that's very, very cool that you have this complex thing in OTel and you're called exponential histograms. You have the new Prometheus native histograms, and they're essentially interconvertible. All right. All the details of it. This is this not a trilogy? It's tetralogy? I don't know what that is. So there are also talks not by me, so it's not just shameless plugs. Again, you can look this up in the PDF that gets uploaded, and you get all the details. How does it even work fundamentally? It's Ganesh talk. How does PromCal change? The performance analysis that was, the TLDR was 10x resolution at half the price, and a whole talk about the OTel compatibility. And it's all from last year. No, this year or last year, right? Yeah. All PromCon, KubeCon, all those conferences. Okay, now hands-on, that was the goal of this talk. How do you use them today, right? Okay, first instrumentation. Best you instrument your Go code, right? Go is just the best, whatever. Okay, Prometheus client Golang is the Prometheus instrumentation library for Go. It had support first, and this is from the previous slide how it works in the classic case. And this is the only thing you have to add. You have to add a native histogram bucket factor, and that's a factor where you essentially say, I want a bucket to grow at most 10% to the next bucket. Bucket over bucket growth at most 10%. So that's how you specify your resolution. You cannot freely pick exactly a resolution behind the scenes. It will pick a schema that fulfills this. So in the real value is 1.09 something, something, something. But this is kind of a more intuitive way to specifying it. I want at least this resolution. And that's it. Then your histogram gets native buckets in addition to the classic buckets, and the normal Prometheus server would just scrape the classic histograms as usual, but if you enable your Prometheus server to scrape native histograms, it will ignore the classic histograms and scrape the native histograms. And then you're kind of done, right? And it's pretty good resolution. Remember the previous thing, that was essentially bucket over bucket growth of 100%, right? At least. Times 2 or even more. And now you have a 10% growth, which is kind of plus minus 5% relative error. It's even a bit less if you do the math, but that has to do with harmonic means and complicated stuff. I mean, at some point you don't want to have this kind of legacy load of classic buckets, so you can just remove them, but then you only have native histograms. So that could be it, but the buckets are created dynamically, so you could create a huge number of buckets here. It's not quite infinite, but almost. This is usually not a big deal, and that is some of the research talks that were linked before. It's one of the lessons that your latency distributions are usually not that broad, and you don't have that many buckets in the end, so it's kind of fine, but some people have fears that they might run out of memory just because of their monitoring instrumentation, which would be bad, of course. It could also be even a security risk, right? We had this discussion about a DOS attack where you artificially try to create a broader latency distribution and then your monitoring system crashes and whatever. Like, if you want to avoid that, you can limit the number of buckets. And there's native histogram max bucket number for it, and I picked 160 because OTel, they have this default. So maybe we just come up with the default in the end as well. This is all a bit in flux. And what happens if you have more than 160 buckets? What the library will first try will just reset the histogram and empty all the buckets, and then they don't exist anymore. That's okay in Prometheus. You can have a counter reset. You just don't want to have it too often compared to your scribe frequency. And this is why you can specify a duration. So do this at most once per hour. That's fine, right? You scrape every minute or every 10 seconds, and then a reset once per hour is you can tolerate that data loss. But what happens if you have to do this more often than once per hour? Then the magic resolution thing kicks in, and you just halve the resolution, or you halve it again if you have still too many buckets. So you pay resolution to limit the number of buckets, it's pretty cool, I think. All right, and now that I told you that partitioning by labels is affordable, let's just turn the histogram into a histogram vector and let's partition it by status code and method or whatnot, right? So that's possible now. I mean, it was possible before, it was just very expensive. All right, in Java, it looks almost the same, just that Java has, instead of this factor, it has this native initial schema, and schema 3 is exactly the 1.09 something something growth factor. So it's kind of a more low-level approach, because internally there's a schema that I would like to not be visible to normal users. So if you go to schema 4, that means you have double the resolution, and schema 5 is again double the resolution. And I think the Java maintainer, I talked to him, it's Fabian, it's also a colleague of mine, and he wanted to add a factor as well. So you can also specify this factor thing. It's a more high-level concept, but otherwise you see how it works. Okay, now you might want to do Go, you might not want to do Go or Java, and then the other libraries don't have support yet, and that's mostly a technical reason, because this is all done with protobuf. Native histograms are very data hungry, and the protobuf, in the way it's designed, is just a natural match to expose those native histograms. That's very cool, and I like it a lot, and that's why Prometheus all of a sudden supports protobuf scrape anymore. Like, it was dropped in Prometheus 2. The talk with the secret history of histograms talks about this. Why did that happen, and why do we have to bring it back now? So it's kind of unrealistic to expect all the other libraries to also support protobuf. So what we are working on is a text representation of the native histograms, which might not be very efficient, but it might be good enough. And like, if you do, let's say, Python, you're probably not in high performance land, and it's probably okay. And this will happen pretty soon, at least we hope so. All right, but there's OTel, right? And I promise it's compatible, and it's a half smiley here because some things really work nicely. You could be in an environment where you instrument everything with OpenTelemetry, and then you somehow will get exponential histograms into your OTel collector. And now you can use the remote write, I think it's called an exporter. The terminology is always a bit confusing. Anyway, the OTel collector can produce the Prometheus remote write protocol and write to a Prometheus remote write receiver, and then it will get auto-converted to Prometheus native histograms. So, nice, right? This is how it should work. There are also more integration points between Prometheus and OpenTelemetry, and one is that the OTel collector can expose a Prometheus metrics endpoint for Prometheus server to scrape. That should work, but it doesn't work yet. There's an issue file for it, so it will work very soon. Hopefully there's no technical blocker here. And there's also the other way around. The OTel collector can scrape a Prometheus metrics endpoint, and then if it finds a Prometheus native histogram, it should create an OTel exponential histogram. Doesn't work either, but it will work very soon. I know that people are working on it. I've chatted with them, and there's an issue open, and again, no technical blocker. What's also interesting, Prometheus in the current version, 2.47, has an OTLP receiver. Like similar to receiving remote write, it can directly receive OpenTelemetry line protocol, and if that contains an exponential histogram OTel, it will convert it into a Prometheus native histogram. Now that's not something we recommend for the normal vanilla Prometheus server, because that means you push into Prometheus server, it's just a single binary, you might get overwhelmed, but there are tons of distributed backends that implement Prometheus API, like Mimir, for example. I mentioned that because that's Grafana's one, but there are more. And they could also, or they will also, and I think Mimir also already does that, have this OTLP receiver. And then it makes total sense to put your OTLP stream into, let's say, Mimir, and it becomes Prometheus native histograms. So that's all very promising. Now let's talk about the vanilla Prometheus server. What do you have to do? The feature is still officially experimental, so you have to enable it with the feature flag, enable feature native histograms. It works since version 2.40, but please use the most recent version because tons of bugs have been fixed, more little sub-features added. So whenever you play with native histograms, just use the newest Prometheus server. There are two more, this is essentially it, but there are two more tweaks you can do. If your Prometheus server also sends stuff out via remote write and you want the native histograms to be sent, you have to tell Prometheus to send the native histograms with this config flag here. This one, config, what is it? Config option. Because the remote write receiver might not know about native histograms. So you have to opt in and say, yes, I know what I'm doing. I will send native histograms. And then there's a nice little tweak here. I told you that a native histogram-enabled Prometheus server will ignore the classic histograms. But funny enough, because the classic histograms all have those magic underscore bucket and underscore count and underscore sum suffixes that I personally don't really like, but they come to our rescue here because that means they don't collide with the native histogram because the native histogram is just the name without any suffix. So you can just ingest them all in parallel. It's, of course, very expensive, but it's a nice migration strategy. If you have dashboards, alerts, anything for classic histograms, you add the native histograms, ingest both, then you can at will migrate your dashboards and alerts, and when everyone is done, you just remove this line, and then you can finally save resources. All right, PromQL itself, that's an interesting thing. How does PromQL change? This is interesting where you see if you just state a native histogram time series with a selector, like a normal instant selector, and usually you would see a floating point number here, but with the native histogram you can actually see a very textish representation of the native histogram with count and sum and all the buckets, so you can literally see this complex new sample type. This should be a nice little graphic, of course, we are still working on that, and then maybe you can drill deeper and see all the numbers, but for now it's just a wall of numbers, but you can nicely see how this works. And then you can do PromQL expressions, and they work normally, right? I mean, you don't notice this is now a native histogram, you can rate it, you can sum it up. Since you have now partitioned everything by method and code, because you can slice and dice, you can select only the 200s. And for example, this one would be a very typical query that feeds into a heat map. We have seen a little heat map, we will come back to this. So you rate the whole native histogram, but you only want to display the successes in this heat map and only the gets, because you want to get this like graphical representation of your latency distribution. You rate it, you sum it, and then you send it, for example, to Grafana and let the heat map get rendered. So now let's look at a few things that you do with histograms beyond heat maps. Quantile estimation is kind of the one killer feature. And first line is the classic case. So we had this new, in 2015, new function histogram quantile, 95th percentile. You have to sum, you have to keep this weird LE label that is very unique to classic histograms, less or equal. It's the cumulative buckets, whatever. Like it's all this complicated stuff about the classic histograms. And then this gives you the 95th percentile over the last 10 seconds, and you can again slice and dice if you have labels. And the new query is the second one. It's just, I mean, no weird LE, no weird underscore bucket. It's kind of as it always should have been, right? So and the histogram quantile will automatically recognize this is now a native histogram and will do the right thing. And we can plot this. I mean, they are very small, but these are the same queries as before. Right side is native histogram, left side is classic histogram, and there is a difference, but that's because the right side is more correct, right? The left side has this, it's I think a 10 or 11, I think it's the 11 bucket histogram from the example, so it's fairly good already for classic histogram standards, but the right side has the 10%. So the error of this estimation is, broadly speaking, plus minus 5%. And you see it has more detail, and you just have to believe me that this is more correct. So that's already cool. Okay, what's really cool is some people say percentiles are all percent lies, and the only true percentile is the 100th percentile, the maximum, right? Or the 0th one, which is the minimum. So, I mean, we all know tail latency matters, so we often do 99.9th percentile or something, but you can go all the way through and have the 100th. I mean, it doesn't matter that much, but if you have such an extreme long tail percentile, you will very easily see a few of outliers with like very high latencies. And in classic histograms, that usually means you hit the highest bucket and then your observation goes into the infamous plus inf bucket. And if you do the estimation, you see there's like a glass ceiling here, right? It never goes above 900 milliseconds. That's because the highest normal bucket is 900 millisecond upper limit. So you don't have any information about this. You hit this, and this is what I was interested in, like what is my maximum latency? And the cool thing with native histograms, whatever you observe, you get your bucket. So this still has a plus minus 5% error, but you see how detailed this is, right? Also time resolution is cool with Prometheus. You can scrape at any interval. And you see 1.2 second, 1.4 second. Whatever it is, you will get the right thing here, which is pretty cool. Okay, average calculation has nothing to do with histogram. This is just a byproduct of the sum and count that you track. Summaries do that as well, so you can always do this. But of course, you also want to calculate averages sometimes, although usually percentiles are better. And this is the old way, because you already had the sum and the count series. It was pretty straightforward. Now, in the new world, the sum and the count are just quote-unquote fields in the histogram structured sample type. So there is a function to extract it, and for technical reason, you have to do the rate first. So this is essentially equivalent. It just, behind the scenes, there's a lot of work. It has to churn through all the data in the histogram. And it also rates, because PromQL, the engine is pretty dumb, right? It doesn't notice that I want to just see the sum. So it rates the whole histogram with how many buckets and sums it up. And here it does it all again because it doesn't recognize that there are the same branches. So this could be optimized behind the scenes, but right now, this is the one use case where the native histograms are actually slower than the classic histograms because they have their series already prepared. You could do a recording rule for that, I guess, but I mean, it still works. It's usually not an expensive calculation, the average. And here again, side by side, it's exactly the same because it's exactly the same data, just stored in different way. Okay, works. Now, fraction calculation, that's the thing that you usually do for SLOs, right? I mean, you could also do like percentile, but usually you say my SLO is that I serve 99% of the queries in 250 milliseconds or less. And then you put a bucket boundary at 250 milliseconds with your classic histogram, and then it's very easy to calculate this fraction of requests, and you can see am I at 99% or not, and you can alert on it and do error budget, burn things, and all those things, right? Now, the disadvantage is if you think, oh, we can actually be better, so let's change our SLO to 220 milliseconds, then you have the whole problem again that now you have to change your bucket boundaries, have to re-instrument everything, cannot aggregate anymore. So with the new histograms, with the native histograms, you have a new function, histogram fraction, and you can just freely define the fraction you're looking for. So you can just change this number and cool. The disadvantage is it's now just an estimate. You cannot say, I want a bucket boundary at exactly this value because it's this automatic schema. So it might have an error of plus minus 5% or something, which made me replace calculation by estimation here. In the context of this, it's usually accurate enough, so that's definitely more pro than a con. And funny enough, for this specific, I picked the 250 milliseconds, so we get exactly the same curve here. Maybe I should have picked something else to see how big the error actually is. But why is this precisely the same? Because the schema, the magic schema, has always a bucket boundary at 1 second or 1 byte or whatever your histogram is about. And then it halves things. It's always about halving, and half of 1 is 0.5, and half of 0.5 is 0.25, and that's by chance a bucket boundary, right? So that's why it's exactly the same, but it would be with slight deviations here. Anyway, this is the typical thing you use for SLO tracking. Update score, if people still use this, I don't know. It is popular enough that we have the update query in the Prometheus docs for classic histograms, the top one here, right? And it's very complicated because they are cumulative, which doesn't play well with the whole update idea. And this query is so complicated that people don't understand it. And we got 5 or 6 pull requests where people tried to fix the query because it's obviously wrong. It took a lot of work to convince them this is mathematically, it's fine. This is update score with classic histograms. But it's really nice with the native histograms, with the fraction, you can really see how update score is defined. It has satisfied latency, which is between 0 and 300 milliseconds. And we take that fraction, and then it has tolerator, which is usually times 4, so between 300 milliseconds and 1,200 milliseconds, and take half of that, add it up, that's update score, right? It's the definition of update score in PromQL, nicely visible. Fine, yeah, that works also well. Okay, now we talked about heat maps. This is one of my favorites. I always wanted shiny heat maps in Prometheus, but with the classic histogram, it never really worked. So this is already a pretty high-resolution classic histogram. And I mean, it looks kind of fancy, but you can't really see anything. And if you now take, this is the 10% growth factor classic native histogram, and look at this structure, right? I mean, you can see so much. You see some weird thing happen here. We have 2 populations of latencies. You can read the stories out of heat maps, right? There should also be exemplars to be click on. I think that works by now, but then you can go directly into your tracing system from that area of the heat map. And I like to say this is like Hubble and this is James Webb or something, like really high resolution, and it tells you so much, right? I mean, heat maps are really cool for troubleshooting and stuff like that. All right, downsides, none, right? Done. Okay, now, I mean, there are downsides. Expect bugs is still a new feature, and talking about bugs all the time. It's officially experimental, so things might still change, okay. But both things get less and less likely. Some PromQL evaluations are still slower, okay. And this is more like where it gets into the concept of this thing. You might have observations that aren't a good fit for an exponential bucketing schema, like latencies, packet sizes, whatever. Most naturally occurring things are like it's a nice thing to have this exponential bucketing schema, but some things are like equally distributed. Then you want more like a linear schema, or they are naturally already logarithmic, and double logarithmic is meh, I don't know. Which is a bit related, you cannot just pick arbitrary bucket boundaries. You might have a histogram that comes from a third-party data source and just says, here are 5 buckets in this histogram with these boundaries, you cannot just mirror that. This is the flip side is you can just use classic histogram for that. If there are not too many buckets, they are fine, and they are perfect for that. So classic histograms won't go away. You can still use it for that. But there's future, so we will come to that. Maybe we have a solution. I mean, we want better graphical representation in the UI. What I have shown you, the heat maps, that was cheating. It was the Grafana heat map panel, which already supports native histograms, but it's in Grafana, and it's also a bit clunky to set up. We, as in my Grafana colleagues, will work on that, but Prometheus should support this natively in its own UI, right? We want instrumentation in all the languages, of course, and this is the cool thing, right? We want custom bucket layouts for special cases. It would break this aggregation idea, this whole guarantee, right? That you can always aggregate if you allow people to introduce weird bucket schemas. But maybe you have this. You have a histogram from another third-party data provider and you want exactly that bucket layout. Or you want, like, you know your SLO will always be 200 milliseconds, your latency for the SLO, and then you want a bucket boundary exactly there. So that might happen. There are way more. These are the three biggest ones. There is a milestone in the Prometheus repo where you can follow the progress and see what shows up there. There are also other repositories that have Prometheus native histogram related stuff. That was also the trouble here, right? It touches the whole stack. Anyway, here we are. On this repo, I link all my talks. You can already see a link to the slides there, so you don't have to wait for the conference website to get them. And that's it. Thank you.